Now in this video we'll talk about a digital to analog converter using a hardware implementation, not the pulse width modulation software implementation that we looked at in the previous one. So we can use a device, and there's lots of them about. This one's called the DAC 5311. Now we're going to have a look at what's inside it and a bit of how it works. In this one it's an 8-bit DAC. So we've got 256 different voltage levels that we can have in our output. It's a binary weighted one, so we talked about that sort of scheme before of how it actually works. And we connect to it via SPI. We'll talk about interfaces like SPI towards the end of this course. But that's essentially how we tell from our microcontroller or other digital logic to this device what analog output voltage to actually produce. So in terms of what it looks like, on the far left there we have our DAC register, which is going to hold the output value that we're actually going to output. Now remember, it's 8 bits that we've got here that we're dealing with. And then with our binary weighted scheme, we have one resistor for each bit. Now we have a whole series of switches there. No switches based on what's in our DAC register. We can switch those on and off. And effectively, as we switch them on and off, we switch in or out those specific resistors and the influence they're going to have on them. We have our reference voltage there because everything within DACs is with reference to a particular reference voltage between our ground or our low voltage and our high reference voltage. And as a result, that goes to our output amplifier, and then that will be our output voltage that we can supply there. In terms of how it looks, they're pretty small. It's only got 6 pins on it, and you can see we've got power and ground pins, obviously. We've got 3 pins that we use for our data transfer, our sync, our D-clock, and our D-in, our data in pin. Now we won't talk about those now because we'll be talking about them later on in the course in terms of serial peripheral interface, how it actually works. And then we have our voltage output, which is our analog voltage output, whatever we're generating, somewhere between 0 volts and the analog full scale voltage that we're going to be working with. Now, how about we do something a bit fancy? How about we create a waveform that looks a bit like this? Rather than just creating something that's nicely stepping up or a sinusoid or something, we can do all those things. But let's create a waveform that's got 5 steps in it. So it'll step from 0 volts to 25% of full scale, 50%, 75%, 100%, and then straight back down to 0 again. So we want to step through each of these values, and you'll be doing something like this in one of the labs using pulse width modulation. And outputting each one for a short period of time. So we get our waveform that looks a bit like this. So let's have a look first at our microcontroller code and how we actually do it. Now we won't go into the specifics just yet of how we actually send SPI code or anything like that. But what we want to do is create a message from our microcontroller to send via SPI a command to say give it 0%. Then we want to delay for a little bit because we want it to be that for a short amount of time, and then send a command 25%. Delay for a bit, send a command 50%, and so on until we get to 100%, and then we go back around to 0. You can see our connection there between our microcontroller and our DAC there, and that serial peripheral interface between the two. And then our DAC will give the output that we want just above, and that's one we've captured on the oscilloscope. Now, the interface we have there is a 16-bit serial string that's being sent. And the way we do it, we've got our clock line that's constantly clocking, going high and low, and that's what we register any data in with, the various clock pulses there. We have our sync line that basically tells our digital to analog converter that we're sending you data now. Here's your 16 bits of data that you want to actually read in and do something with. And then we've got our data bits that are actually being sent. Now, of those data bits, the 16 bits of data that are being sent, the top 2 configuration bits and things like that. The next 8 are our data bits. Remember, this is an 8-bit DAC, so we've only got 8 bits that we're specifying our voltage levels with, and the rest of the bits for this particular DAC are unused. Now, they do that because you could upgrade to a higher resolution DAC, and your higher resolution DAC will use some of those extra bits. And so you don't actually have to change a whole lot of your interfacing and things like that. They've clipped it at 16 bits, and that allows you to future-proof things, to change your DAC and put a 12-bit DAC in there, for example. And you'll have the same effective data structure, but you'll have more of those bits dedicated to actually encoding the data, encoding what actual analog output voltage you'd like to have. So that gives you a good example of a hardware implementation of a DAC and how it can be used.